Come on. Okay. Okay. I tend to refer to this week, or this section we have here, 6.3, is like the um, climax of a class in a way, just because it covers the material that personally I find of the most interesting in terms of what can be done to make algorithms in numerical linear algebra um, both um, efficient and also reliable. And um, some of the uh, ideas that I'll be laying out this week, more so on Wednesday. So today kind of sets the stage for it. I When I was learning about these things as a student, I found them to be quite ingenious, and I think it went a long way towards um, inspiring me to go deeper into numerical linear algebra. What I found is that um, when it comes to learning about other people's work in this field, and numerical analysis in general, and also numerical linear algebra in particular, I found that I'm not very easily impressed. But I was impressed. I was impressed when I first learned about this work I'm going to show you this week. Um, Now, once you're exposed to it, hopefully it won't be a letdown. Um, but I think this is something that's well worth paying attention to the details of, because it's a great example of what can be done in numerical linear algebra to make great strides in uh, algorithm development and getting around what might appear to be insurmountable obstacles. Okay. Um, Now, um, where we left off is from the power method, we arrived at a um, surprisingly simple iteration called a QR iteration, where you compute the QR factorization of A, and then you just multiply the factors in reverse order, which works because RQ, well, if you look at this equation and rearrange it, you find that R is equal to Q transpose A, because Q is orthogonal. So if I use that in here, that means that the new A is Q transpose AQ. And because Q is orthogonal, Q transpose is Q inverse. This is a similarity transformation of A, so it has the same eigenvalues as the original A, but is hopefully something that is closer to upper triangular form. So, and I demonstrated this to you in MATLAB last week, that by carrying out this repeatedly, we do get something that is approaching upper triangularity. So here we do have an algorithm that will compute all the eigenvalues of a general square matrix. Um, and But this is really a good start. And it doesn't always succeed, but in most cases it will. But the problem that we have, and I'm going to address this week, is that um, this approach, while generally workable, is far, far too slow. Um, okay. So we're going to work on this. We're going to make modifications to it to try to speed it up. And the result of all this is going to be a very famous algorithm in the field called the QR algorithm. And it's famous enough that it was named one of the top 10 algorithms of the 20th century because of how ingenious it was. And It was developed in the early 60s by Bob Francis. And actually, one thing I want to check about that, because I believe that he was not the only one. Ah, yes. Okay, so and I want to give credit where credit is due. By Vera Kublanovskaya. Okay, and it's unfortunate, but also very much a sign of a time, sadly, that people tend to give credit just to Francis. In fact, a key component of this algorithm is called a Francis QR step. But let's see. Oh wait, sorry, and it was not the not the early '60s. It was the late '50s. It might have been published in the might have been published in the early '60s. Okay. Okay. So Francis in 1959. Okay, so this is why I remember 61. So she came independently of Francis's efforts in a couple of years later. Okay, and I don't know. I hope I didn't say Bob Francis. It's actually John Francis. Okay. Whoops. All right. And okay. Now, what's interesting about Francis is he had, after this work, not too long after he developed the QR algorithm, he left the field of numerical analysis. He worked in National Research Development Corporation in the UK, and so he left the field long after that. So he had no idea that he was famous in the field. That he came up with this algorithm, and that was universally used within numerical linear algebra, and so it was my advisor, Gene Golub, who tracked him down in 2007 after he had retired, and he was able to appear at a conference to mark the 50th anniversary, and so 2009 of the of its development. So it's got to be kind of weird to discover after so many years, like, oh yeah, by the way, you're famous. So, but that's what happened. Okay. Now, so first, I need to describe from original matrix A, what eigenvalue revealing form are we going for? It's called the real sure form. So we're going to assume, for simplicity, that A is a real matrix. So it may have complex eigenvalues, and that's something we're going to have to spend some time dealing with on Wednesday. But at least we know that they're complex conjugate pairs if they do. Now, it's very important priority for reasons I've mentioned earlier. We want to avoid complex arithmetic. So if A is real, we want to do only real arithmetic till the very end, and obtain eigenvalue revealing form of A that is still a real matrix. Just because complex arithmetic is significantly more expensive than or slower than real arithmetic. So if we do QR iteration, then if we carry out this, for instance, if A is real, certainly the QR factorization will also be real. Then multiplying these two real matrices will also produce a real matrix. So if the A has complex eigenvalues, the Shor decomposition will be complex. It will have complex entries along the diagonal of upper triangular matrix T. So there's just no way to get a complex matrix from the operations that QR iteration would perform. So the QR iteration, we start with an operation like this. We come up with some orthogonal matrix Q naught, and we carry out this. So if this is real, then we just compute the QR factorization of this and multiply the factors in reverse order over and over again. Again, nothing complex will come from that. So in this case, this algorithm will not produce the actual Schur decomposition. But that's okay. What we can get instead is a matrix of this form that is at least block upper triangular. So we get a real Schur decomposition. Q is a real orthogonal matrix, and T is real. And block upper triangular, where all the diagonal blocks are either 1 by 1, if it's a real eigenvalue, or 2 by 2 if it corresponds to a complex conjugate pair of eigenvalues. So we can certainly get this. So that's what we're going to aim for. And this is something that is at least attainable. And once we get to this form, then each of those 2 by 2 diagonal blocks, we can easily get the eigenvalues of those to get the 2 complex eigenvalues in the complex conjugate pair. So that won't be a problem. Okay. So what we could do is carry out this iteration, and at least until enough subdiagonal entries are 0 so that any blocks along a diagonal are either 1 by 1 or 2 by 2. And because what would happen is if we keep going, there are certain subdiagonal entries that will not go to 0, no matter how many times we keep going. But as long as all other ones are 0, once we get down to 1 by 1 or 2 by 2, then that'll be good enough, and then we can stop. Okay, so this is the real Schur decomposition or real Schur form that we're looking for. Okay. So now that we have an idea of what kind of matrix we're trying to get, and we know that the QR iteration, as I've described it, will get us there eventually, the goal now is how to make it reasonably efficient, because at this point, it's not. Oh, dang it. Stop it. No, I do not want to enable Siri. Okay. Okay. So the first big problem with the QR iteration, it's extremely slow. Each iteration costs too much because we're computing a QR factorization that takes order n cubed operations, and then we multiply these two matrices together. That is also order n cubed operations. So we're incurring order n cubed work per iteration, and then it's quite a matter of how many iterations we perform. So in fact, at this point, it's too many. So we have too many iterations, and each iteration costs too much. What we're going to focus on today is the issue of at least making each iteration less computationally expensive. What I'll focus on Wednesday is how we reduce the number of iterations so we converge to this real Schur form more rapidly. So what are we going to do? What we'd like to do is start by performing some similarity transformation of A, something of this form, so that this matrix H, which has the same eigenvalues as A, can be we can carry out QR iteration on H instead of A, so this process can proceed more efficiently. Now, since we end up computing QR factorization of H, if it's already almost upper triangular to begin with, we would that would be great because then this part would not take much work, and then hopefully this would not take much work either. Now, one might think, well, what if we just go ahead and compute the QR factorization of A and use this matrix Q for a similarity transformation. It turns out that, well, it might seem like a logical choice because Q transpose A already is upper triangular. The problem is you have to multiply by Q on the right also. So this part may be upper triangular, but multiplying by Q on the right will destroy that structure. So to get a clear idea as to what's going wrong, so that we can fix it, how are we going to compute the QR factorization? Well, we learned a few approaches. There's Gram-Schmidt, there's Givens rotations, there's Householder reflections. So I'll just focus on one of those approaches, a Householder. So if I work on A to make it upper triangular, I use a Householder reflection that zeroes out most of the first column. So that's a first step toward making it upper triangular. So what will happen is P1 transpose A has a first column that is almost entirely zero. Well, then what happens? Then I multiply on the right by P1, and that will undo the zeroing that happened but when multiplying by P1 transpose on the left. Now, why does that happen? Because when you are trying to zero out the entire first column except for the first entry, so entries 2 through n are 0, that will change all the rows of A when you're multiplying on the left. So then you multiply by P1 on the right. That will affect all the columns of this matrix. So this matrix may have the first column that's almost all 0, but then because multiplying by this will affect the first column, those 0 entries will not be 0 anymore. So all that work is wasted. But it does give us an idea as to what we can do differently to not have this negative outcome. So let's try this. Suppose we use a householder reflection and we zero all entries of our first column again, except the first 2 entries. Well, to do that, we don't need to touch the first row. This would only affect rows 2 through n. So then, when you compute this, you multiply by P1 on the right. That will affect columns 2 through n. It won't touch the first column. So here you zeroed a bunch of entries in the first column to get this. Then, after you multiply by P1, those 0 entries will still be 0. So this is much better because so what happens is you end up being able to zero a whole bunch of entries below the diagonal. Not all of them, but most of them. Okay. So if we can continue this process, so like we go to a second column and zero out, so we keep the first 3 entries, so zero out entries 4 to the bottom. Then what we end up with is a matrix called a Hessenberg matrix. So a Hessenberg matrix is similar to an upper triangular matrix. So in a Hessenberg matrix, Hij is 0 if I is greater than j plus 1, whereas in an upper triangular matrix, it's 0 whenever I is strictly greater than j. So we have everything in the upper triangle. We have one subdiagonal that has non-zero entries. Everything below that must be 0. So what we can do is we can use a sequence of householder reflections, P1, P2, up to Pn minus 2, because everything in the last 2 columns can stay non-zero. We're only zeroing entries in the first n minus 2 columns. So here's the algorithm that will give us a Hessenberg matrix. Okay, so it's called Hessenberg Reduction. All right. So what we do is it's similar to QR by householder. We use a householder reflection that works on, for each column J, it works on rows J plus 1 down to the end. So for instance, when J is equal to 1, it'll affect rows 2 to n. It won't touch the first row. So here we're applying a householder reflection on the left to H, and then we're applying that same householder reflection on the right because it's a similarity transformation. And then here we're accumulating all the householder reflections to make the matrix U. So that'll be needed if we want all of a Schur decomposition, not just the eigenvalues. Okay. Now, this function that it calls house, we've seen this before. This computes a vector v that is used in the householder reflection. So your householder reflection has this form that will zero out all entries of a vector that it's applied to except for the first one. So here we apply it to rows 2 through n of column 1. So entries 3 to n will be 0. The second entry will be allowed to remain non-zero, and the first entry in that column also, because it's not even touched. Okay. Now, this is an expensive algorithm. Like it's similar in expense to the QR factorization, somewhat more so, because it's applying householder reflections on the left and right. So it takes order n cubed operations, but it's only performed once before iteration begins. And the rest of the algorithm will take order n cubed operations anyway. So this is an acceptable amount of effort for a pre-processing step, if you will. All right. So now that we see how we can use a similarity transformation, something of this form, to reduce A to upper triangular form. No, that's completely wrong. Reduce A to upper Hessenberg form. We need to take a look at what's involved with computing a QR factorization of a Hessenberg matrix as opposed to a general matrix. Okay. All right. Now, the nice thing about a QR factorization of a Hessenberg matrix, the only non-zero entries below the diagonal are in the first subdiagonal. That means that you only have to zero out one entry per column. So it's a lot less work to compute the QR factorization of a Hessenberg matrix than a general matrix. So there's only n-1 entries to zero out, so you just need n-1 Givens rotations. Each one of these affects 2 rows, so order n operations each. So the total will be order n squared operations. So it saves an order of magnitude work to go to the trouble of reducing A to Hessenberg form at the start, and then during each iteration where you need to compute QR factorization, you're doing a whole lot less work. Now, to reduce the Hessenberg matrix to upper triangular form, you use these Givens row rotations. You're applying them on the left. Then you have to multiply that resulting matrix R by Q on the right. That means applying all of these Givens rotations on the right that rotate columns. So that's the same amount of work as it was when applying on the left. So the whole process, computing H equals QR, then H equals RQ, all of that takes order n squared work. All right, so here are the details of that. So here's the original Hessenberg matrix H. You apply these Gibbons rotations on the left. Now, remember, as I've said so often, transpose of a product is a product of a transposes in reverse order. So that'd be the same as G1. Notice the order here is reverse of what's here. All of that, transpose H. So all of this together makes Q in the QR factorization. So that's upper triangular. And then you apply those same rotations on the right. So I take my R and multiply by G1, G2, and so forth. These same matrices are just not, just not using a transpose anymore. So here we have row rotations applied on the left, column rotations applied on the right, and now this matrix, this is upper triangular. This will destroy that upper triangular structure, but it'll still be Hessenberg. So if H comes in Hessenberg, and we do a QR factorization of it multiply in reverse order, the result will still be Hessenberg. That's very important that we keep that structure so that each iteration will be efficient. Now, and you can convince yourself that this new matrix coming out of this process, H tilde, is in fact Hessenberg by considering which columns are affected by applying these column rotations. So, for example, the first Gibbons rotation that I apply to H will affect rows 1 and 2. So then when I apply it here, it's going to affect columns 1 and 2. Well, if R is upper triangular, the first column has only one non-zero entry. The second column has 2. So if I rotate them, the first column will have at most 2 non-zero entries, which is what a Hessenberg matrix has. And you keep proceeding, seeing what each one of these rotations does, and you can see from that that the result has to be a Hessenberg matrix. Okay. So this whole process where you take a Hessenberg matrix and you do H equals QR, then QR, H tilde equals RQ, that whole process is called a Hessenberg QR step. So now I can show you the algorithm for Vats. Okay, so what we do is you go through all the columns except the last, and in each column we have the in column J, only the J plus 1 entry has to be 0. That's the subdiagonal entry. So we find a Gibbons rotation that will do that. And then we apply it on the left to rows J and J plus 1. Now these have to be saved during this loop so that they can be applied later. So after we reduce H to upper triangular form, we do H equals QR. Then we update Q by applying all these Gibbons rotations, and we also apply those same Gibbons rotations again on the right to the columns of H to carry out multiplying RQ to get our new Hessenberg matrix H that hopefully is closer to upper triangular form. All right, so yeah, we do have Hessenberg in, Hessenberg out, but the intent is to slowly make those subdiagonal entries go to 0 to reveal the eigenvalues, and that's the step. That process of trying to zero those entries is something I'll talk about more on Wednesday. Okay. This function Gibbons we've seen before. that computes a cosine-sine pair, so that okay, so that this matrix applied to these two entries of from a matrix H will cause the second one to be zeroed. Now, one thing to keep in mind is the implementation point is if we're doing row rotations, technically those affect the entire row, but some portions of those rows will be zero. Because as we're going from left to right through the columns, like if we're working on column J, these entries of columns 1, 2, 3 up to J minus 1 will already be zero. So that's something that should be kept in mind when carrying out all of these rotations. And in fact, okay, let's see. Yeah, that was not done. Okay, that was done in this case. Like here, I'm only working on columns J through N. Because we're rotating these rows, J and J plus 1, but only these columns are affected because these entries to the left of column J are already 0. I didn't really take that into account here, but this is something that can be improved about this algorithm, that only certain rows need to be affected when carrying this out. So like I mentioned earlier, coming into this loop, H is upper triangular. What I'm doing is column rotation. On the first column, only the first two entries can possibly be non-zero. So that's something that I would. Oh, wait. I'm sorry. That is taken into account. Yes, because this is a column rotation. So normally it would work on all rows, but I only go rows 1 to J plus 1. So the entries that could possibly be non-zero. So this is why I'm doing that restriction. It's very important to pay attention to the structure of the matrices you're working with. Which entries are known to be 0? You want to avoid performing operations on those entries needlessly, because we're dealing with particularly large matrices. That those kind of wasted operations can really add up. So even though it has no effect on the correctness of your algorithm, if you don't take it into account, it can be a lot slower than it needs to be. Are there any questions up to this point? I look at the Teams window, I just see 9 blocks. It's like the Brady Bunch, in a way. Or Hollywood Squares or something like that. Or maybe you're all just tuned out. I can't tell. You're welcome. Okay. Now, as we're carrying out this QR iteration, we do H equals QR, then H equals RQ. What will eventually happen is that some subdiagonal entry of H will turn out to be 0. And that's a very good development, because what that means is the matrix becomes block upper triangular. It has a structure like this. So this entry right here at the upper right corner of his 0 block became 0. So now we can focus on finding the eigenvalues of H11 and of H22. So when you're carrying out a QR iteration, you may start out by working on the entire matrix, but you don't want to do that from beginning to end. You need to focus on a portion of this matrix that is said to be unreduced. So an unreduced Hessenberg matrix is one that has all subdiagonal entries non-zero. So if an entry becomes 0 and gives you this kind of structure, you want to pick one of these and continue working on it. Because if this is the only non-zero entry, only zeroed entry, all other subdiagonal entries non-zero, then both of these blocks would be unreduced. So be sure to work on a unreduced block by selecting the appropriate rows and columns. Because you need to keep an eye on the subdiagonal entries. As they become 0, that's opportunities for further decoupling. The problem gets smaller and smaller. Because you're expending order n squared work per iteration, and that can be quite a bit if n is large. So anytime you can cut that value of n is a very good thing. And then and you keep zeroing subdiagonal entries until you can't anymore. So then you have that real sure form, and you can stop. But one thing to be careful about, hold on. Okay. You have to choose a maximal unreduced diagonal block. So you can think of it this way. You want to find a, you think of H as having a structure like this, where H22 is unreduced. But you have like a 0 and a subdiagonal here and also here. So that's how you ensure that you're finding correct eigenvalues, because the eigenvalues of H come from the eigenvalues of H11, H22, and H33. I should point out that the size of this block or this block could be 0. Like if the entire matrix H is unreduced, then H is just H22, and you have nothing here. But as you proceed with a QR iteration, and you start getting 0 entries along a subdiagonal, then you start to have a structure like this. So you want to find the largest unreduced matrix that you can and keep working on it. And eventually you'll have nothing left. Now, one property about unreduced Hessenberg matrices will turn out to be quite useful to us. It's called the Implicit Q Theorem, which sounds like something out of a James Bond movie. And what it says, there's a lot to unpack here, but the idea is it's basically a uniqueness result for the Hessenberg reduction. So if Q and V are two orthogonal matrices, both of which reduce A to upper Hessenberg form, and if this one is unreduced, and if Q and V have the same first column, so both Hessenberg reductions start out the same way, but it turns out they're essentially the same. Now, not exactly the same, but if Q1 and V1 are equal, then all the other columns, they're plus or minus each other. And also H and G are equal, at least in absolute value. what's particularly important here is that whatever, if H is unreduced and G is also unreduced. So they have our zero, non-zero entries in the same places. So the term that we use for this is they're essentially equal. So the columns of Q and V are basically in the same direction. It just might be exact opposites. So each column of Q might be plus or minus the corresponding column of V, and at least the entries of H and G have equal magnitude. Now, the full impact of the implicit Q theorem won't be realized until Wednesday, but actually, okay, I do have time. I want to give you an idea as to how this theorem is proved. So, okay. So if I have Q transpose AQ is equal to H, and I can rearrange this to get A is equal to VGV transpose. So if I multiply both sides on the left by V, multiply by both sides on the right by V transpose, I get this. So then I can take this form of A and substitute it in here. Okay. So I have Q transpose, VGV transpose, Q is equal to H. Now, but what I can do is if I group these together, V transpose and Q, then this right here is the same as V transpose Q transpose from the oft-repeated property of a transpose. Transpose of products is product of transposes in reverse order. Now, I can label this matrix, I'll call it W. Okay. Now, so now we have is I can rearrange this to give GW equals WH. Because W is a orthogonal matrix. Very important point, a product of orthogonal matrices is also orthogonal. We're using that in many places, and it's particularly helpful here. So now I have this relationship. Okay. Now G and H are, they're both upper Hessenberg. Okay. Okay. So now what I want to do is I want to look at the first columns of these. So what we have here is GW1, which is the first column of W. That's equal to a first column of E1. Now H is Hessenberg. So the first column of H has two non-zero entries. So that would give me W1 H11 plus W2 H21. Now, but the first column of W, that's equal to V transpose times the first column of Q. Now, V and Q have the same first column. And because V is an orthogonal matrix, all other columns of V must be orthogonal to Q1. So this vector is all zeros except the first entry, which is a 1. So this is because of Q and V having the same first column and both having orthonormal columns. That's very important. Okay. That's why, because what is this? This is the inner product, dot product of all columns of V with Q1. Q1 is a unit vector. First column of V1 is Q1. First column of V is Q1. Therefore, the first entry is a norm of a unit vector, which is 1. All other columns of V are orthogonal to Q1. That's why all the other dot products are 0. So that's how you get E1. So now what we have on the, if we go back to this equation now, I have first column of G is equal to all this. Now this is also E1. Okay. Now, I don't know what W2 is at this point. I know that G in H of Hessenberg, but because G is a Hessenberg matrix, only the first two entries of this vector are non-zero. Now, so if I rearrange this, I'll move the first term to the other side. So now, if I look at this vector right here, only the first entry of this is non-zero. Only the first two entries of this are non-zero. Therefore, only the first two entries of W2 are non-zero. Okay. So the first column of W has one non-zero entry. Second column of W has two non-zero entries. So jth column of W has only the first j entries non-zero. If you have a matrix like that, column J has only the first j entries non-zero, what type of matrix has that structure? What kind of matrix must W be then? So first column has 1 non-zero entry, second column has 2, third column has 3, and so forth. And ever at the top.
Upper triangular?
Yes, W is upper triangular. But W is also orthogonal. So W inverse, which is equal to W transpose. Well, if W is upper triangular, V inverse is upper triangular, but the transpose is lower triangular. So V inverse is both upper and lower triangular. So W has to be diagonal. Now, each diagonal entry of W is a dot product of columns of column V and column Q, but these are unit vectors. Okay. And because each column of V, by virtue of its being diagonal, has to be orthogonal to all other columns of Q, and vice versa, then these vectors must be parallel. And because they're unit vectors, their dot product must be plus or minus 1. So that is what, and Vj equals plus or minus Qj. And then finally, because each entry of the two Hessenberg matrices has this expression, and similar for the Hessenberg matrix G, but with V. And because the Q's and the V's are plus or minus each other, then the entries of H and G must also be plus or minus each other. So they have the same absolute value. All right, so that's a proof of the implicit Q theorem. Okay. And everything comes from understanding where the entities you're dealing with have to have zero entries or non-zero entries. Okay. Also, the assumption that H is unreduced is important. That's what guarantees that this is non-zero. That's important for that. Okay. All right, so that's one useful property of Hessenberg matrices. The Hessenberg reduction has this form of uniqueness in a way. Another property that's helpful is that if H is an unreduced Hessenberg matrix, the first n-1 columns have to be linearly independent. That's something that can be proved by an inductive argument. Keep in mind, again, where the columns have non-zero entries. And this is important because if a matrix has full column rank, the QR factorization is unique. If it turns out that if H is an unreduced Hessenberg matrix, its QR factorization is also unique, even if it doesn't have full column rank. So that's going to turn out to be important to us because of it's important to know that no matter how we go about computing a QR factorization of H, the result will be the same. Okay. So because when you have matrices that are rank deficient, you have to do pivoting, kind of like a Gaussian elimination, where you end up with a zero entry somewhere, and you need to interchange rows. QR factorization is similar. I didn't really cover that, but if you have a matrix that's rank deficient, to do QR factorization, you do what's called column pivoting. You rearrange the columns of A to get the right structure. But it turns out there's no need to do anything like that here. We could just do straightforward QR factorization as I had covered, like using Givens rotations. And at least we have that assurance that this is going to work, that it produces the one and only QR factorization. Okay. So at this point, what do we have? We have a somewhat speeded up QR iteration. So if we take the time to reduce the matrix A to Hessenberg form first, then do a QR iteration where you compute a QR factorization and you multiply the factors in reverse order, each one of those iterations will take only n squared operations instead of n cubed. Now the convergence is still too slow. There's still too many iterations, but at least now each iteration is an order of magnitude cheaper than it was. So that is significant progress. So what I will talk about on Wednesday is now how can we modify this algorithm to reduce the number of iterations and get this convergence to quasi upper triangular form faster. And that's going to be the tricky part. But these properties of unreduced Hessenberg matrices, that there's this uniqueness to how they're transformed, there's uniqueness to their QR factorization, that's something that will be very helpful to us in making the changes that we need to, and having confidence that that they will work. All right. So I've come to the end of that. So we have time for questions on this or any homework questions. Quiet bunch as always.
I have a question.
Okay.
I'm still stuck at expression 532.
Okay. All right, I'm going to. Okay, I need to adjust my sharing here.
Yeah.
Okay.
So like when hj plus 1j is 0, then it means that the matrix is now a square matrix, no longer n by n, right?
Oh, wait. Okay, so if we go here, no, all it means is wait, Which matrix are you referring to?
Since the H tilde, the last column there is 0, right?
Yeah, yeah. So we're just going to deal with this, just with HK.
Yeah, isn't that a square matrix?
Yes, it is. Oh yeah, well, this is square anyway. This is not, but yeah, but what would happen is you have no need to work with this. Instead, you would just have this.
Yeah, so which means the solution is no longer we're no longer trying to minimize residuals, right?
Right, because in this case you can solve AX equals B exactly.
Yeah.
And you can use the fact that both A and HK are invertible.
Yeah, I try to use that, and I'm not really sure if it got anywhere. Like I multiply both sides by A inverse, like you suggested.
Mm-hmm.
Then I came to a point where I had a matrix multiplication that I couldn't really factorize. So when I did that, I got X to be equal to A inverse B minus B naught times A inverse QK E1 HK. And since E1 is a vector, I couldn't really push it out, so I can get A inverse QK HK and then substitute for QK.
Well, the thing is, if you use both the inverses of A and HK,
Yeah.
then since the solution you're looking for is A inverse B, and where you can use the fact that the first column of QK is related to B from V's equations. So that gives you a way to work B into it.
Yeah, I did that. And I
Okay.
tried working B into it. If you scroll back down a little. Can you scroll down a little?
Okay.
Yeah, so our solution will still be in this form: xk equals x0 plus qk yk, right?
Right.
Yeah,
Yes,
that.
it would still have this form.
Yeah. So I'm not really sure. I tried doing that, but still, I came up with something I couldn't make sense of. I worked B. I worked B into it. I tried working X into it also. Since X is A inverse B, I felt maybe we could also substitute for X in this.
Okay. Hold on a second. All right, so this is equal to. Okay. Mm, all right, so minus. Mm, all right, so all right, so from this,
Yeah.
after working with the inverses as best you can, um, oh, and I promise you this does work. um, that if you consider if you take the first, because what you have is a matrix equation, but then if you take the first column only of a matrix equation, and so then what you'd have on the right side is just the first column of QK multiplied by everything's, and by expressing that in terms of B, then A inverse B will appear. That's giving you X. And then you can solve for X.
Yeah, so A inverse B appeared.
Yeah.
Which I substitute for X.
Right.
But the other expression that involves QK multiplied by E1, which is on the first column of QK, I wasn't really sure what to do with it. Like it was, I don't know.
Wait, QKE1?
Yeah.
Okay.
Is that the first column of Q?
Okay, because once you work B into it, that should not have still been there.
Okay.
Now, on the left side, you're gonna have, because that's where something involving HK will appear, and then you're taking a first column of that. So it seems like something went wrong if even after getting A inverse B to appear, but you still had a
QKE1.
Yeah.
Okay.
Yeah.
I'll take it. Yeah.
Seems like a factor got dropped or something.
Okay, I'll take a look at maybe.
Okay.
For the next class, I should have something.
Oh. All right.
Thank you.
Yep. A couple minutes. Anyone else? Oh, someone already left. Yeah. Okay, oh quiet ones. I will see some of you in PDE. I'll stop the recording here.